Okay, so what we're going to do today is we're going to start in on a new chapter, chapter 11, which deals with similar shapes. And that's actually a really pretty big idea in geometry. It's something that we're going to spend a good bit of time on. And it does come up quite a bit on the state assessment, the test you have to pass in June. So, pay attention. So, similar polygons. It says, you know that figures that have the same shape and size are congruent figures. We've talked about that quite a bit. Figures that have the same shape but not necessarily the same size are similar figures. To say that two figures have the same shape but not necessarily the same size is not, however, a precise definition of similarity. And so they use the example of the funhouse mirror and say, well, this guy right here is the same shape but a different size as this guy and that guy. So are all those things similar? And it turns out that mathematically speaking, no. This little dude right there is not similar to that dude right there. It is not similar to that dude right there. Okay? And so we're going to get into a more precise mathematical definition of why that's the case. Okay? So start with a little question. Are all rectangles similar? They all have common characteristics, but it turns out they're not all similar. And what we mean by that mathematically is that you could not enlarge or reduce a given rectangle to fit perfectly over every other rectangle. What about other geometric figures? Are all squares similar? Are all circles similar? Are all triangles similar? Exciting times. We're going to figure all that out in this lesson, chapter, something. Okay, so like I said, rectangles A and B in this example here are not similar, and that's because if I was going to take B and try and expand it so that it would fit over A, I would need to expand all of the sides at the same time. And since this side right here is already about the same size as that, when I expand this side to try and make it match that one, these sides are going to get bigger also, and it's not going to fit on there. Okay? So you could not enlarge or reduce one to fit perfectly over the other. So rectangles A and B are not considered to be similar. Similarity comes up in movies. It says movie scenes are scaled down to small images on strips of film. Then they're scaled up to fit a large screen. So the film image and the projected image are considered similar. And as it turns out, not surprisingly, if the distance between the projector and the screen is decreased by half, each dimension of the screen image is also cut by half. So this dimension right here would be twice as big as that one there, and this dimension right here would be twice as big as that dimension there. Pretty nifty stuff. Okay, so then you're supposed to do a little investigation, which we skipped, but we, in the process, come up with a definition of similar that you might want to write down in your notes, and that is right here. Two polygons are similar if and only if the corresponding angles are congruent and the corresponding sides are proportional. And so what you need there is all the angles of both shapes have to be exactly the same, and then the sides have to all be in the same proportion. In other words, if one side is twice as big as another side, then all the sides on the shape have to be twice as big as the other one. And the little symbol that they use for similarity is that little squiggly guy right there. So that says corn is similar to peas. That means that angle C is the same as angle P. So this angle right here is the same as that one right there. Angle O is the same as angle E. Angle R is the same as angle A. And angle N is the same as angle S. So they're all in the same, the order of the letters tells you which segments and angles correspond. So I could also do the same thing looking at the segments instead. So for example, if I take the first two letters in the shape corn, CO, then that means that this side corresponds to this side over here. And they have the proportions set up right there. Since we know that they're similar, I know that if I take the length of side CO and divide it by the length of side PE, I'll get the same answer as if I take the length of OR and divide it by side EA, or if I take side RN and divide it by side AS, or finally if I take side NC and divide it by side SP. Okay? And then we can also do that same thing comparing sides within the shape themselves. So instead of going crisscross here and dividing the sides of one shape by the sides of the other shape, I could also take these sides right here and go CO divided by OR. And as long as I divide by the corresponding sides of these two shapes here, like PE, which would be PE and EA, I will also get the same answer. So I can go from a side of one shape to a side of the other shape, or I can go this side divided by that side in the same shape would equal this side divided by that side in the same shape as well. Okay, so the question then is, do you need both conditions, congruent angles and proportional sides, to guarantee that the two polygons are similar? For example, if you know only that the corresponding sides of two polygons are congruent, can you conclude that the polygons must be similar? Or, if corresponding sides of two polygons are proportional, does that mean that they're similar? In other words, if you know the angles are the same, does that mean the sides are proportional? Or if you know that the sides are proportional, do you know that the angles must be the same? Well, it turns out the answer to both of those questions is no. So for example, if I look at this rectangle right here, or this rectangle and this square, obviously all of the angles are the same because they're all right angles, but the sides are not proportional. So if I take this side right here and divide it by that, 12 divided by 18 is 0.6 repeating, and then if I compare that to what I get if I go that side there divided by that, 12 divided by 10 is 1.2. And since 1.2 does not equal 0.6 repeating, that means that these two shapes are not similar. So just because the angles are the same does not mean that the sides are in the same proportion. And then I can do the same thing but opposite for the sides being proportional. So now I'm going to compare this square to this rhombus. And obviously if I take that side there, 12 divided by 18, and compare it to this side here and that side there, those proportions are going to be the same. 12 divided by 18 obviously equals 12 divided by 18. But you can see, since this is a square, that has 90-degree angles, and this one has both 120 and 60-degree angles. So those two shapes are not, in fact, similar. Okay, so we can use this to find missing sides. So we know in this case that shape SMAL is similar to side BIGE. So we want to find X and Y. So what I'm going to do is I'm going to identify this side right here and that side right there as being two corresponding sides that we know the measurements of. So I know that all of the sides are going to be in the ratio of 18 to 24. So if I want to find X, I'm going to start with this side over here, 21, and compare it to X right there. And notice that the two numbers that are on top came from this shape, and the two numbers that are on the bottom came from that shape. That has to be the case. So 18 divided by 24 is going to equal 21 divided by X. So in order to figure out what X is to solve proportions, I cross multiply the two numbers that I know. So I'm going to go 24 times 21. And when I do that, I get 504. And then I need to take that answer and divide it by the number that's left over, the one I haven't used yet. So I'm going to divide that by 18. So 504 divided by 18 is 28. So X equals 28. Then I'm going to do, and then Y is an angle, so that's even easier. because the angles of similar shapes have to be the same. So if this is 83, then that also has to be 83, and I am done. Okay, let's try another one. Think, in this case, is similar to large, and I need to find a bunch of missing sides here. And this is a pretty easy one to do because since T and K, first letter, last letter, match up with L and E, first letter, last letter, you can see that this shape right here, all of its sides are twice as big as that. So that means if this side right here is 3, then that one has to be 6. If this side right here is 5, then this side has to be twice as big, or 10. And if this one right here is 2, then that has to be twice as big, or 4. Then to find Kn, since that's on the other one, we have to go backwards. Since this is 12, I'm going to cut that in half this time, and that side is going to end up being 6. So that is an easy way to use similarity to figure out all those things, okay? All right, and then we also might be asked to figure out whether polygons are similar or not. And so the first thing we're going to do is look at the angles. This angle has 2 slashes and this has 2 slashes, so they're the same. This has 1 and this has 1, so they're the same. This has 3 and this has 3, so they're the same. And so that means that this last angle has to be the same as well, because they all have to add up to 360, and so what's left over has to be the same. So we got all the angles are good. Now we have to see if the sides are in the same proportion. So I'm going to compare 150 to 165. And then I'm going to compare 180 to 192. And then I'm going to compare 120 to 128. And I'm going to look at 140 and compare it to 154. And what I have to get is when I divide each one of those, I need to come up with the same answer each time. So 150 divided by 165 turns out to be 0.90, repeating, I guess. Then 180 divided by 192 does not come out to be the same thing. That's 0.9375, and so I can stop right there. It does not matter what this side rate proportion is and what this proportion is, because all 4 of them would have to be the same for those shapes to be similar. And since this one right here does not equal that one right there, I can stop and say no. Okay, now again they tell us that these 2 shapes are similar, and they're trying to trick us this time by rotating the shape a little bit. Ooh, how do we figure out what goes with that what? Okay, well this side here goes with that one because SP are the first 2 letters in spider, and H and N are the first 2 letters in honeycomb. So those 2 sides go together, so my ratio of all these sides is going to be 88 over 66. So I'm going to use that to figure out what HB is. So that's going to be 36 over HB. So just like I did on the other problem, cross multiply the 2 numbers that I know. So 36 times 66, and then divide by the one that's left over. And that tells me that HB has to be 27. And turns out that I got carried away there, and I thought we were just doing notes, but what I've done is started to do the assignment for you instead. And the notes ended all the way back here with this example. So there you go. So you got a little head start on your assignment. So what I meant to do was stop right here when I was done with the notes and give you an assignment to work on. So I'm going to do that right now. Whoopsies. Okay, so we are in chapter 11, so we're going to go with page 585. And let's do 1 through 16, 18, I just did some of the problems from your assignment for you. Didn't mean to do that, but I guess it doesn't hurt. So you can get started on that. And we'll take questions later.